than usual weeks since you're going to be gone on Friday for e-learning day. The quiz we're going to take on Thursday, and there's going to be a reading assigned for Friday. The reading and all the homework will be posted up today, so you can actually get the e-learning assignment done early, which is totally fine. That way you can have a 3-day. It's going to be reading.
Oh, the homework too?
For Friday, I'm going to assign a reading, but it'll be available at the end of the day today, so that way you can get it done early if you want to. Okay. There is some homework up and all that other good jazz. However, what is officially going to be assigned for e-learning is that reading. Okay. We're going to do periodic trends, advanced electrons, a couple different things. All right, I gave you a fresh periodic table today. All right, and what I want you to do either on your periodic table or on the fresh one I gave you, write the number of valence electrons at the top. All right. So the first column, we've got 1, 2. We skip the middle ones, 3 through 8. Do you want a fresh one, Annie?
Yes, please.
Absolutely. Some of them are a little rough and ragged, so.
Thank you.
All right. We skip the D block. All right. So you got 1, 2, all the way across. 3, 4, 5, 6, 7, 8. There is a small little caveat in there, but we'll talk about it in a second. All right. All right, so valence electrons, what are they? They're the electrons on the outermost shell that is with the atom. All right, those are the ones that pretty much are involved with the chemical reactions. So we're looking at electrons at this point. We're really not going to be looking at too much what's underneath the hood, underneath the valence shell. We're going to look at what is just on the surface and is willing to play with each other. And that's the valence electrons. So right across the top, we see 1, 2, 3, 4, 5, 6, 7, 8. All right. And then across the top, there should be some group numbers. I'm going to talk about groups in a second, but groups also help you determine the number of valence electrons, but they are not the same. Okay. So this is right here. This is not group 3. All right. So don't follow the group numbers, which some people like to do. This is group 13, which is why I tell students, hey, just write across the top. 1, 2, 3, 4, 5, 6, 7, 8. Okay. Finally get some light outside.
Is the quiz and the homework from last, like the week
Before fall break.
Is that in this, like, 9 weeks? Or, so, like, I redid it. It wouldn't do anything for my grade, right? Because you can't put it in. Okay, so it's not.
I cannot change any grades from last 9 weeks. For the most part, unless there's any small mistakes, your grade that's in School G is the grade that's in Harmony right now, and that's the grade you'll have for the 9 weeks. And I think congratulations. I don't think anybody ended up with lower than a B. Ooh, I want to say that. If it is, it's a very, very small handful of individuals. So across the board, you guys are doing great. All right. Don't quote me on that, but I looked at the grades very quickly. All right. And I didn't see anybody with some grades I was unhappy with. So across the board, you guys are looking great.
Is the homework hard?
The homework is just like we're about to do here.
Okay.
Okay. So looking at our periodic table, let's find how many valence electrons each element has. So we got hydrogen. How many valence electrons is hydrogen going to have? 1. That's it. You just look at the count. There we go. What about sulfur? 6. So we go over here, find sulfur. It's got 6. What about neon? 8. Xenon? 8. Oxygen? 6. And boron? 3. Okay. That's it. You just look at the column, see how many valence electrons it has. These are what they are bringing, willing to come play with. Hydrogen has 1 electron it is willing to play with. It'll either give it away, all right, or it'll bond with something else, all right. But boron, on the other hand, has 3 electrons it's willing to play with. Okay. Sulfur has 6. We'll talk about neon and xenon while they are special cases. As we unpack chemistry, we're going to talk more and more about special cases, and I'll talk about what those special cases here in a second. But first thing you're going to do is use your periodic table. Look at how many valence electrons it is. Good there? Questions, comments, concerns? Pretty easy so far? Breaking in that fall break crud. Am I going to move on? Okay. This is the same picture, so nothing's different. Okay. We're going to take those valence electrons and then figure out what will tend to happen. So the octet rule. How many legs does an octopus have? 8. So oct meaning 8. So the octet rule is based off of 8. So for the most part, and there's a reason I underlined and bolded, tend. Elements tend to follow the octet rule. Either they love to be full and have 8, or they love to be empty and have 0. So, there are in-betweens, but we really don't talk about that too much. It's what's it really prefer to be at, like what makes it happy. All right. So we're going to look at the number of valence electrons, and then we're going to see what will it tend to do. And once you get there, oh, okay, this is actually not that bad. Okay. I'm going to scroll down just a little bit. I'm not going to go to the next one anyways. All right. So the valence shell is the most outermost shell. That is the period you're in. So this thing's not working for me today. This is, period 1, period 2. This shell you're in either likes to be all the way full or all the way empty. Doesn't really like to be in between. Okay. So just when you do this, ask yourself the question. Is the number of valence electrons closer to 8, closer to 0? And then what will it tend to do? Morning, Mr. S. Doing all right. Did you have a good break?
Yeah, can't complain. Doing all right.
Good.
How yourself?
That was full.
Yeah, that's what I said.
All right, Dawson, you ready?
Yep.
Help me out again. How many valence electrons does hydrogen have again? As 1. Is 1 closer to 0 or is it closer to 8?
0.
Closer to 0. So hydrogen will much rather prefer to get rid of that 1 electron rather than try to pick up a full shell. Okay? So if hydrogen prefers to get rid of an electron, what charge will it form then if it gets rid of an electron?
Positive.
+1. So hydrogen prefers to form a... These markers aren't working today, and I'm pretty sure I just made that one not work forever. Okay. Hydrogen tends to make a +1 charge. You good, Aubrey? You ready for the next one? Let's go to sulfur. How many valence electrons does sulfur have? 6. Is 6 closer to 0 or closer to 8? 8. So sulfur really prefers to take on 2 more electrons to get to 8, right? So if I gain 2 electrons, what's my charge? -2. -2. On a roll. We good there, folks? You want a sucker? I got Jolly Rancher and Tootsie Roll in hand. You want a sucker though? Now let's look at neon. Maddie, you ready?
Nope.
Nope? Hopefully you're joking. All right, let's look at neon. How many valence electrons does neon have? 8. Is 8 closer to 8 or closer to 0? 8's closer to 8. It's happy. It doesn't want to do anything. So it doesn't want to gain or get rid of electrons. So what charge does neon like to make? 0. It doesn't like to do anything. It's inert. It just likes to chill. It's a loner. It likes to be by itself. So if we scroll on down, find xenon. What's the same thing there going to be, Maddie? We got Xe, xenon,
So it's 0.
0 again. So let's take a quick step back there. If it has 8 valence electrons, what charge will it tend to form? 0. So everything in that column tends to have a very particular charge. And what is that? For this one on the way right side, it's 0. I'm going to take a step back there. Let's do oxygen now. Amy, you ready?
Maybe.
Let's try it. Ready? Oxygen. How many valence electrons does oxygen have?
4 or 6.
6. All right, so we got 6 right here. So is 6 closer to 8 or is it closer to 0?
8.
Closer to 8. So it wants to gain 2 electrons.
So it's -2.
Fantastic. So oxygen prefers to make a -2 charge. You interested in dum-dum?
Yes.
My throws have been off today. I didn't practice over break. Welcome. All right, Kingston, you're next.
Okay.
Boron,
That's 3 valence electrons.
3 valence electrons. So what charge would you like to perform?
Plus 3.
+3, that's it. Good here? All right. Really, that's what it is this is getting into chemical bonds, which we're not going to talk about this week. We're going to talk about in 3 weeks. But I want you able to do this part pretty quickly as the week goes on. Yeah.
What would 5 be?
5?
Yeah.
Like nitrogen?
Yes.
So if we did nitrogen, how many valence electrons does nitrogen have?
5.
5. So the charge it likes to perform is what? Well, if we're at 5, is 5 closer to 8 or is it closer to 0?
Never mind.
I know where your question's at, and I'm going to go there next, okay? But so if it has 5, what charge would it like to make?
3,
Close.
4.
Uh,
Wait.
If we have
Oh,
5
wait.
valence electrons, we would prefer to gain 3.
So it'd be -3.
The charge it would form would be a -3 charge. So now, Hannah, is your question going to be what we're going to do with the 4s? Or do you have a different question?
No, I have something different.
Okay. Was your question deal with the 4s?
Yes.
What do we do if we have 4 valence electrons? Like carbon. Carbon's tricky because based on its environment, it is kind of indifferent. It can either lose 4 or it can gain 4. And so based on its environment, it'll either lose or gain 4. But I'm not giving you any questions like that on your homework or quiz or anything like that. Because all the ones with the 4 column, they're tricky. That's that special case that I'm talking about. As the more chemistry you study, the more special cases we do. I'm really not going to unpack those too much. We're going to keep it simple. All right, if you want to study advanced chemistry, you save that for next year, okay? Hannah, what's your question?
So like with boron, even though it's 3, and it would probably get rid of 3 electrons to become positive.
Yeah.
Will it ever try to gain them to become 8?
It can, but it takes a lot of energy.
Okay.
It's what does it tend to do? What is the easiest state? Chemicals in the world are really lazy. They like to be in the lowest energy state. They like to go the easiest route. They don't want to do the high energy, most difficult routes. Can you take boron and shove 5 more electrons into it to make it a full shell? Yes, but that's under very special circumstances and a lot of electricity going through it or energy.
Okay.
So that's why I'm saying that the key word here is tend to do, and we're going to stick with that tend. However, there's one special caveat in this whole thing. Helium. How many electrons does helium have? What's the atomic number of helium? 2, so it can't have 8. How many electrons make the first shell full? Count across. 1, 2. Follow me there? So the first shell, which only can hold 2 electrons, all right, which is why helium's on this way right side. Even though It's on the way right side. It only has 2 valence electrons, but what charge does it like to form? It likes to form a 0 charge. Follow me there? If we try to think about it and we say helium has 8 electrons, hopefully in your gut that just feels weird because it only has 2 protons. All right? So, like I said, there's those special cases. Okay? But are we good on the examples we did here? Okay. All right. Let's unpack this a little bit. We're going to use what we now know about charges and valence electrons, and we're going to unpack the periodic table and use some very specific words. Across the top, on those new ones I printed out for you, and I'm pretty sure they're on the old ones too, you should have numbers across the top, and there should be numbers going down the side. If not, we wrote them in definitely. Okay. The numbers going across the top are your group numbers. The elements are grouped by their similar properties. And then periods go across. So the periodic table is arranged by grouping patterns and I would say properties as well. So the vertical columns, which are called groups, we now know you can predict its valence electrons. We're going to look at how we can predict atomic size and ionization energy. And then horizontal rows. All right. They have shells. We can figure out valence shells, and we're going to use that for atomic size. So now we're going to look at atoms and what their electrons want to do. But we're going to look at how does that change the size of it? Does it make it bigger? Does it make it smaller? What happens? So what you can do in your notes is, as we're looking at the trends, I'm going to draw a couple of arrows. You're welcome to draw those on your periodic tables, or in your notes, draw like a blank periodic table and just do some arrows. Okay? Either one's totally okay. We're going to look at trends and what they tend to do. By the end of this, we'll understand a little bit why cesium, when you throw it in water, or rubidium, when you throw it in water, it violently reacts. And why is that? Why does it want to get rid of that one electron so daggone much? And why fluorine is the most selfish element on the entire periodic table. It wants to rip electrons away from whatever it can. So hydrofluoric acid, acid that has fluorine in it, is one of the most corrosive acids, and that's because it wants to rip electrons away. So when you pour acid on something, it's ripping electrons and protons, and they're thrown in all different directions. So by the end of this, we're going to understand why. These ones really want to get rid of those electrons, and fluorine really wants to get some. And then this whole row right here, why they just don't want to do anything. They're the loners of the periodic table. Good here? All right, I'm going to draw, there's going to be some arrows drawn. You don't have to, you can do it on your periodic table or you can do it in notes. You good, Dawson? I see you right still. Am I good to move on? Okay. All right. I'll be here for a little bit. I'm not going to move too fast. So look at atomic radius. How big an atom is. The problem we run into is that you can't really know for certain how big an atom is, but man, we get pretty close to predicting it. What do is we look at two atoms that are chemically bonded together. Here's the nucleus of one and nucleus of the other. When it's chemically bonded, they're sharing those electrons. And so what we found out is if we measure this space right here between the two nucleuses of two atoms, right, we can say that half of this distance is the size of one atom. But the problem we run into is that there's stuff that doesn't like to react with anything. So we can't even truly say what the size of all these noble gases are on the way right side, because they don't like to react with anything. They just want to be loners. They're by themselves. They like to bounce off the walls, and that's it. Okay. So when we're looking at an atom's size, it's determined by its electron clouds. It's what those electrons are doing. So if we were to go out to the football field, and I were to put a quarter on the 50-yard line, that quarter would be the nucleus. That's all our protons and neutrons are at. The electron cloud would be the football field. That's how big and how wide those electrons like to swing. So what the electrons are doing determines how big or how small the atom is. So let's look at the group trend. All right. All right. As the shells are filled, more electrons are added to the cloud. So, yeah, I'm just gonna say that. So on your periodic table here, what I want you to do is I want you to draw an arrow to the left and down. So this is where it gets a little counterintuitive. You're gonna turn your imagination brain on. Dawson, help me out again. All of the ones on the way left side have how many valence electrons? One. They have one valence electron. Do they want to keep that one, or they tend to kick it away? Kick it. Oh,
never mind.
they want to kick it away because it's closer to zero. So man, what do they do with that one electron? They're saying, I really don't want to hang out with you. I'm going to put you as far away as possible. So the size of the atom gets bigger if they're pushing the electrons away. However, fluorine on the way right side wants to gain one. And it really likes its 7. So what does it want to do? It just wants to bring another one in and hold it close. So as you go to the left and down, you increase in size. You're going to have to kind of turn on that thinking brain when you're doing the homework. All right. As we add or remove electrons, what happens? Okay. So atomic radius. Good here? We're going to do 2 other trends, and I believe we're done for today. You have a question, Aubrey? Okay. Am I good to move? Yeah, Hannah.
You might have already said this, but when you move to the left, you're losing protons, so how would that increase the size?
When you're talking about the period trend, we're talking about across here. So going from here, from here to here, we're increasing the number of protons. It's just getting bigger in general. When you're going to the left, you have to think about what does it want to do with those electrons. Well, this half of the periodic table wants to get rid of their valence electrons. Those electrons are way out and way out on the side. What do these ones want to do? They prefer to gain their electrons, so the ones they have are closer. Does that make sense? But as we move down, you're increasing the number of protons, and there's another shell underneath that outside layer.
Okay.
Follow me here. I'm gonna draw a picture, and then well, hopefully this helps out. So if we have the first shell filled, right, and then we move down to a next shell, that next shell inherently is bigger. It has to go on the outside.
Mm-hmm.
Follow me there? So as we move down, we're increasing shells. The shells are getting bigger. Well, if we are, let me erase this a little bit. Actually, no, I might be able to use this picture. If I have, no, this is where it's been fighting me today. Let's try this again. First shell can hold 2 electrons.
Yeah.
All right. Well, if I'm lithium, I got 3 protons, 3 electrons. it really wants to get rid of that 1. So what is it going to do with this 1? Man, it's going to put it really far out there. Oh, this is where it's been fighting. Let's try this again. So it's gonna want to kick that 1 out there. How does it kick it out there? It expands that second shell a little bit wider. And so instead of it being right here, it's out here. Does that make sense?
Mm-hmm.
It
So-
rich wants to get rid of it.
So any element on the far right, can they do the same thing but bring it in?
Yeah, so if we look at fluorine, where is it going? Get out of here. Fluorine, it's very close to here, but instead of 1, we've got, I'm about to put my foot through this board. Do it, somebody said really quietly. We got 1, 2, 3, 4, 5, and 6. Okay. Sorry, fluorine, we got 7. Well, fluorine really likes to have that 7 close because it's almost full. It's almost happy. So it's going to hold those electrons in a little closer. Follow me there? It also has more protons to pull those electrons in. What does fluorine want to do? Well, it just wants to pick up 1 more electron and it's happy. And it's full. Does that make sense?
Does fluorine have 9?
Fluorine has 9 protons.
Oh, never mind. Okay.
You good?
Yeah.
All right, fluorine, but it has 7 valence electrons. Cool.
Mm-hmm.
This is, I think this is really interesting stuff. Man, it can be like a little mushy in the brain for a little while. Okay, we good here? All we got to know is you go to left, go down, atoms get bigger. This is why cesium, I don't know, why is he going to the racer all of a sudden? There we go. Cesium is a very, very big atom. And it has 1 valence electron. So when you throw it in water, water picks up that 1 electron so quickly, you cause an explosion. So that's why cesium is so big. Fluorine, however, is really small comparatively. And that's because it has its 7 valence electrons. It really likes to be at 7, and it's just going to pick up 1 more and have its nice, compact, nice, neat family. So from here, we can now look at a couple other trends. Ionization energy, which is the opposite of atomic size. How much energy does it take to remove an electron?
Hold on. That says the opposite of what this one says about increasing.
Which one? Can you rephrase the question a little more?
That one, the arrow points to the right, it was increasing, but earlier it pointed to the left. Is that not the point?
So this first relationship is atomic size. This next relationship is ionization energy. So that's the energy it takes to rip away an electron. It's just a different relationship. This one, cesium, is a really big atom. But man, it is wants to get rid of the electron so much, it doesn't take very much energy.
The bigger the more that they want to get rid of.
Yeah, that's kind of a good correlation there. And then fluorine, remember it's really small. Man, it likes its 7. The energy it takes to rip an electron away from fluorine is so much because its 7 is nice and close. They really just want an 8th one and they're good. So, the energy needed to remove an electron. As you go up and as you go to the right, it's easier. However, this is a trend. Who's the special case in this whole thing? The way right side. They have 8 or 2. Their shells are completely filled. Right? They're happy. Right. So this one still takes a lot of energy to remove stuff. Right. So when we look at trends, it is not for certain, it is not for sure. So what I recommend you don't do is try to look up these values because it's going to be way in depth. So when you're doing the homework, just follow the trend what's here. Okay. So as we go across, we add our valence electrons in. What does it want to do? Well, the first half of the periodic table, on the left side, they prefer to lose those electrons. It doesn't take much energy to kick those electrons away. However, once you go to the right side, they prefer to pick them up. Man, it takes a lot of energy to pull another electron away, because what they want to do is they just want to gain. So hopefully now we can understand why a lot of things in the world that prefer to get rid of electrons, like sodium, and prefer to get electrons, like chlorine, you find in everyday life. What's sodium and chlorine put together? Sodium chloride? What is it? I'm going to bet some of you had it for breakfast this morning, especially if you had eggs or hash browns. Probably not cereal, though.
Water?
Salt. Sodium chloride, which is sodium and chlorine. Sodium prefers to get rid of that electron. Chlorine loves to pick it up. So that chemical bond, sodium chloride.
So sodium chloride is just salt.
The salt you sprinkle on your food, not the salt you put out in your road. That's a different kind of salt. We get here in ionization energy, which go up and to the right.
Do we draw those arrows on?
Yes, I'll draw the arrows on your notes or on your periodic table. Well, just draw, and make sure if you're drawing all on the same one, you label which one's which. So I would say ionization energy on these arrows. If you just draw a bunch of arrows on your periodic table but don't label what they are, you're going to get confused. So any good? You ready to roll? Did you have a good break?
Yeah.
All right, last one. Electronegativity. How much does that atom want an electron? We're going to look at atomic size and electronegativity in depth. We're really not going to do too much with ionization energy. So how much does that atom want an electron? Cesium really wants to kick it away. Fluorine really wants to pick it up. And then we're going to unpack this a little more when we talk about chemical bonds. Ionic bonds, covalent bonds, metallic bonds. Okay? And that all has to deal with what those electrons tend to want to do. I'm going to go back real quick, but I believe, oh no, we got one more slide after this, and then we're done for today. Okay? But this is actually the last note of written slides. Okay. So as we go across the right, those atoms want electrons more and more and more. As you go up, they want electrons more and more and more. Let's ask the question, why does iodine have a lower electronegativity value than fluorine? Can we agree fluorine and iodine both have 7 valence electrons? They got a 7 right at the top. They both want to form a -1 charge. But why does fluorine want it more than iodine? Well, that's because iodine already has 4 shells that are completely full. It has 4 layers under its hood. It is totally happy. How many does fluorine have? Fluorine only has 1, and it's a small one to begin with, and it really wants to have 2 full shells. So it's really hungry because it doesn't have much underneath its hood to make it happy. So what we're going to do is we're going to unpack this. All right. I'm really going to try to find some nice labs for us to do this week that will unpack some electronegativity stuff. I just haven't found much anything that I prefer. I found some activities, but I didn't like them. So. But now we know that we have the capability of doing the homework, which is looking at trends. And here's what I want you to do when you do the trend. I'll ask about one type of trend. I'll say, list these following atoms in atomic size from largest to smallest. And it'll be a random list of 5 or 6 different elements. So if I give you try this again. Nope. If I give you cesium, cobalt, carbon, and helium, list them in terms of their atomic size. And just go with that picture we had earlier. All right. So atomic size, we go to left and down. So which one's the smallest one first? That'd be helium, according to what we have. Next on that list, as I go down, we run into carbon. Cobalt would be next. And then cesium would be the largest. So you'd list them in that order of 1, 2, 3, 4. Okay. So when it comes to trends, I just want you to have this kind of gut feeling what's going on. We're not going to look at the values here. So if we look at really closely, you can see that the numbers beneath these ones are very specific. So fluorine's electronegativity value is 3.99. What does that mean? We're not going to unpack that. So we're not going to look at actual values. Because the only point of looking at actual values, if you look at things like called partial polarities and just some stuff that we're not going to do. All right. We're going to look at it qualitatively, not quantitatively. Same thing with ionization energy and atomic size. We're not going to look at the actual numbers, but overall, what does it tend to do? So now we might be able to understand some special cases. All right, it's a gray background, you don't have to write it down. Okay. So if you look at the periodic table, we can now understand why the noble gases are called noble gases, because they don't react with anything. They have a full valence shell. They have 2 or 8 valence electrons. They like to have 0 charge. They just bounce off of stuff. The only way to get those electrons to do anything is you have to shoot them with electricity, and then they glow. Halogens, way right side, all have 7 valence electrons. They have a -1 charge. They love to form salt. So almost every salt you find in the world, table salt, road salt, a couple other salts, Epsom salt, all right, are using the halogens. So almost any salt you find in the world will be in that column. All right. Alkali metals. Now hopefully you understand. If you throw them in water, they get rid of that electron so fast they explode. And I looked into it, and we can't do it. Dawson, I'm pointing at you because I know you asked about it. It was just way too expensive. All right. And why hydrogen it is so special. It is probably the most special and the most abundant element. It only has 1 valence electron, so it loves to have a +1 charge. But it can also have a -1 charge based off of the environment. It's a nonmetal, but it's on the left side of the periodic table. And why is that? And that's because it has properties of both left and the right side. Okay. Okay, so that's all we got for today. All right, we're looking at trends, kind of what happens. The homework's pretty straightforward. The reading is up already. All right, you can get started on that if you want to. And then tomorrow I'll have an activity for us to do. I think we're going to look at some values and do an activity with it, but we'll see if I get the stuff before then. Okay.